So in the second part, we want to prove that the interior of S contains all other open subsets of E that are contained in S. So another way of saying that, and an easier statement to kind of get your head around and prove, is that if U is open, and also if U is also contained in S, so if U is both open and contained in S, then that together implies that U is a subset of the interior of S. That is to say that U is contained in the interior of S. So remember, if we want to show containment, if we want to show that U is a subset of S, then we have to show that if X is any element in U, then that implies that X must be in the interior of S. So we have to show the following. If X is in U, again, which is any open subset that is contained in S, then that implies that X is in the interior of S. So this is what we will show. We will show this. Okay, so let's do that. So let's go off first of what if X is in U, what does it mean for X to be in U? So if X is in U, well, we know that U is open, and we're going to just leverage the definition of an open set again. Remember, an open set is, or rather, a set is open if for each X in that open set, there exists an open ball entirely contained in that set. So I have a set here, and if I'm saying that this set right here is open, then any point I choose in here, like say if I choose this point, then by definition, since this set is open, there must exist an open ball centered at that point that is entirely contained in this outside set here. Maybe I should have done a different color. That's contained in this blue outline here. If I pick any point, then there must exist an open ball entirely centered at that point, entirely contained in this blue set that I've outlined here. So if X is in U, and since U is open, then that implies, by definition, that there exists an open ball with center X, I'll call BX, so I'll say an open ball with center X, and again, I'll call this BX like I did before, but this is a different BX than from what I did before, so don't get confused by this one and mix it up with what we did in part 1. This is entirely independent of part 1. So there exists an open ball with center X, and I'll call it BX, such that BX is entirely contained in U. That is to say that BX is a subset of U. Saying that something is a subset of something else, so saying that BX is a subset of U is the same as saying that BX is contained in U. And that's also the same as saying that U contains B sub X. Okay, so if BX is contained in U, then look at what this shows. Check this out. There's another fact that I know about U. Well, U is contained in S. So check this out. U is contained in S. That means, since BX is contained in U, and U is contained in S, so here's my BX here, here's U, and then here's S, so BX must be contained in S. So therefore, and this is just one possible geometric interpretation for this statement. This is not what it always looks like, but just to give you kind of some intuition behind what this statement feels like, I guess, as in a picture form. So BX is contained. That means that BX is contained in S. BX is contained in S. And remember, X is just any point. X is just any point in U. And any point in U must have an open ball centered at that point, entirely contained in U. So therefore, and since U is contained in S, any point in U must have an open ball centered at that point, entirely contained in S. And therefore, look at this. Based off the definition of the interior of a set, X, based off the definition of interior set, S is all points X such that there exists an open ball with center X contained in S. And look at this. There exists an open ball centered at X for each point in U, as we've just shown, that's contained in S. So therefore, X is in the interior of S. And since X is any point in U, we've just shown that any point in U must also be in the interior of S. And therefore, we've shown what we wanted to show, that is that U, any subset that's contained in S and it's also open, must also be contained in the interior of S.